All right, so last time we stopped off starting about the OSI model. Here is the OSI model again. Application, presentation, session, transport, network, data link, and physical. Remember I told y'all need to know that pretty much back and forth. And make sure you know the numbers too, because some of the questions on the test might say they might say this is a layer 3 protocol. They're numbered from 1 at the bottom to 7 at the top. The application layer is layer 7, the physical layer is layer 1. And a great example of why you have to know those numbers, if I say a layer 3 switch, for example, then you know that switch I talk about is operating in the network layer, which later you'll learn means that it's a managed switch, so it's got an IP address, because all of your IP addressing takes place at level 3. So each of the layers now we're going to go over kind of briefly, and then later in the other chapters we go into more detail about each of the layers. But the top one is the application layer, and it facilitates communication between software applications and the lower level. It doesn't actually include the software applications themselves, it is the protocols they use. For example, if I'm talking about web traffic, I don't care at the application layer if it's Chrome or if it's Firefox or if it's IE, but I do care that it's HTTP traffic, because HTTP is an application layer protocol for transmitting web traffic. So software applications negotiate with application protocols. And here they give the example I just talked about, HTTP. So here what they're showing is that the application layer kind of sits below the software, and it sends information to the application layer for it to deal with. The presentation layer is right below that. It accepts data from the application layer, and it formats the data. It translates it into different file types that might be used. Examples here they give, the presentation layer deals with the formatting of graphics files, which are GIFs, JPEG, and TIFF files. It also deals with streaming media like QuickTime and MPEG files. One important thing to know at this layer, this is where encryption happens. That is a question I got on my test several years ago when I took it. At what layer of the OSI does encryption take place? That's the presentation layer. And the example they give here, SSL, which SSL is what HTTP uses to be secure for you to communicate with like banks and things. So here they're taking and they're showing one more step in our same graphic. I've got a web browser that talks to an API that then sends HTTP traffic that is then decrypted and encrypted with SSL or TLS or whatever encryption we're using. The session layer is below that, and the session layer coordinates and maintains communication between the two network nodes. The connection for ongoing data exchange takes place here. An example they give is the connection between a web browser and a web server. So this is also where what is called a keep alive takes place. And that is what keeps a communication link open when one is created. Even though encryption is handled at the presentation layer, the session layer makes sure that that encryption stays in place. So if it's an encrypted page, it makes sure that it continues to be encrypted. Synchronization takes place here. Synchronization is the process where for computers to be able to communicate on a network, they've got to have the same preferences set up, like the size of what they're going to transmit, things like that. The session layer determines when it's ended or what needs to be restarted. So here is their example of a session layer for voice communications. And this is just basically what happens with like a VoIP call. A request call goes over. The phone on the other end says, yes, it's okay for us to communicate. Then still there, that's two keep alives where data is going back and forth. Finally, an end request goes, and something that doesn't happen when you hang up the phone but does happen in the computer world, an okay, I received your end request will end the communication takes place. So the transport layer is below that. The transport accepts data from the session layer and it manages end-to-end delivery. It also handles hardware flow control. If it is a connection-oriented protocol, this is where the three-way handshake takes place. And we talk more about what that three-way handshake is later. This is a good place to make a note on this, though. There are two types of protocols, connection-oriented and connectionless. And the difference in the two, connection-oriented is called reliable. It uses this thing you're going to learn about called a three-way handshake before anything is sent. And basically that three-way handshake means that both parties send data to each other and set up a communication link, then send the data they've got to send and then break it back down. Connectionless protocols are called unreliable, but I don't like the term reliable and unreliable. I just want y'all to know them because you're going to see it. Unreliable doesn't mean that it's not used. Actually, there's a lot more connectionless or unreliable traffic on the internet now than reliable. And the reason is connectionless traffic is a lot faster because it does not waste time setting up all that three-way handshake. Connectionless traffic relies on upper levels to make sure the data gets there. But because it's faster, that's where all your streaming media comes from. If any of you have ever listened to a radio station on the internet or you watched a Netflix movie, you've used UDP, which is a connectionless or an unreliable protocol. And because of sites like Netflix and Hulu and all, there's more traffic now on the internet that's unreliable than there is reliable. I read something just a few days ago that they estimate Netflix, Hulu, and YouTube use about 53% of the entire bandwidth of the internet now. Which, yeah, it doesn't surprise me either because what do I do when I have 5 minutes of free time? I get on YouTube or Facebook or Hulu or watch part of a movie on Netflix. So lots of people are doing that. At the transport layer, the checksum string also takes place. And what a checksum is, there is a field in a packet when it's sent out on the net where the checksum is stored. It is a mathematical formula that's run on the data that's in the packet, and it returns a number. When the packet is received on the other computer, it runs the same mathematical formula and looks to see if it got the same number. If the number matches, it assumes the data, received is legit. It wasn't changed or wasn't altered in transmit. So it's good. If that number doesn't match what's in there, it assumes it got garbled and it asks for it to be sent again. With connectionless protocols, you don't establish the connection before transmitting. And here again, they're saying they're faster than connection-oriented. Other things that happen at the transport layer is segmentation. And segmentation is something that is very important because it breaks up these larger packets of data into smaller packets that can actually be sent out on the network. Let me give you just an example. When you go to like bipsy.com or bipsy.edu's webpage, that graphic at the top of Bipsy's page is, I don't know, maybe 25 or 30K in size. It's not very big. But all that Ethernet can transmit at one time is 1,500 bytes. So that 30K picture has got to be split up into probably 60 or 70 data packets to be sent out on the network for you to receive it. All of that's taking place here at the transport layer. It breaks everything up into packets that are the right size for whatever the media is. And a term you hear is MTU, your maximum transmission unit. And that is the largest unit the network can carry. With Ethernet, the default is 1,500. What kind of internet connections do y'all have at home? Cable or DSL? Cable. Who else got cable? Everybody, you got DSL? One thing you can do to speed up your DSL connection is go into your router and see what your MTU is set at. If it's at 1500, if you lower it to 1491, the speed on your DSL connection will increase. And the reason for that is that DSL uses what's called PPPoE, or PPP over Ethernet. And that adds an 8-byte header to the front of an Ethernet packet. So if you leave yours set at 1500, every packet your computer generates to send out on the network has to be broken into 2 more packets to be sent because they're too big. They would then be 1508, so it's too large. When you cut that down to 1491, what actually happens, you're making the Ethernet packet smaller, but it's just the right size after that header is added that it can go out in one packet on your DSL modem. So if your DSL ever gets sluggish, check that out. That's something you can look at to speed it up. On the other end, the transport layer handles reassembly. It puts those little packets we just talked about back together. And it also adds a number to those called sequencing. And the reason for sequencing is because the way the internet works, you know, all of your data may not go out the same path. Once you get data out on the internet, routers look at traffic everywhere and they try to determine the fastest path to send data. Well, if a router has 2 connections and one of them gets saturated, it'll switch over and send data out the other one. It is possible because of that and because the internet is so vast that if we're communicating over a large distance, the packets will arrive at your computer not in the order I sent them. So that sequence number allows the computer to say, oh, this one goes here even though it's out of order, so it puts it back together so that what you get is the right order for what it was sent in. So here they're kind of just showing segmentation. A long message, transport layer breaks it up. In their example, they put every character in a different packet. It gets sent over the network. The other end takes it and puts those packets back together so that you have what was originally sent. We're going to look at a program called Wireshark later. And all of these things that you see that look like this on the screen now will make a lot more sense in Wireshark. But here they're showing what a TCP segment actually looks like on the network. And all of those flags are binary numbers that are set that mean something different. For example, in that one, you see that the flag is set for a sync and an acknowledgement. That would tell me from looking at it that that is part of the 3-way handshake. I know that that is TCP traffic. Up at the top, I know that it says port 80, so I know that that's a request about a web page. So the network layer is below that. And the network layer translates network addresses into its physical counterparts. It describes how to route the data. It handles addressing. This is where our IP addresses come in. And there are 2 different types of addresses you need to be aware of. A network address, which is also sometimes called a logical address, that is the IP address. But then every network card on an Ethernet network also has what's called a physical address. And this is one of those areas where, because the industry uses more than one term, the test will. A physical address, a hardware address, and a MAC address are all the same thing. And as I describe this to y'all, you will hear me mix all of those up. And I'm kind of doing that on purpose to make sure that you are aware that those all mean the same thing. So if I asked you a question like, tell me the MAC address on your computer, and then I asked you 2 minutes later, tell me the physical address, the answer you should give me for those should be the exact same thing. So here is just an example of a network address and a physical address. And that's just a typical IP address, 10.34.99.12. You'll notice that the MAC address is in hexadecimal. And do you all know what hexadecimal is? Okay. In networking, you have IP addresses that use what is called decimal. The numbering system that we use as humans is a decimal address. 10 digits, 0 through 9. Hexadecimal uses 16 digits instead of 10. But we do not have a means, we don't have numbers that represent anything above 9. You know, think about it. If you want to write the number 10, you can't write that with one digit. You need 2. So in hexadecimal, we use the letters A through F to represent numbers 10 to 15. So you see that's why in that hex address you see 0060, 97 3E, 97 F3. I don't know why my computer's doing that either. You saw it just move and I didn't touch the mouse. Do what?
Might be on slideshow.
Oh yeah, it could be set to automatically move on. I need to see if these are.
So E would be 50 or something?
Do what now?
E would be 50?
E would be 15.
15.
0 through 9, 0 through 9, and then A through F. And that is just a way to make more numbers. We use the alphabet to explain that, just because we don't have symbols in our language that go beyond the number 9.
16, so A would be what, 10?
Right. A would be 10. B would be 11.
C 12. Yeah, I got it.
Right. So routers fall into the network layer. So one of the most common network layer protocols is, of course, IP. I'm going to talk about a few others so that you're aware of them, that they exist. But we live in a world now where IP rules everything. And the internet has a lot to do with that, because IP is a standard protocol. We all adopted that standard protocol so we could communicate on the internet. Remember from last time I said think about a protocol as a language. We've got to have some language in common to be able to communicate. Well, IP has kind of allowed everything to be able to communicate with everything. So fragmentation subdivides the transport layer segments. That's performed here. Segmentation is preferred over fragmentation for greater network efficiency. Here is what an IP packet looks like on the network. And you see up here at the top, you've got a source destination, a source address, and a destination.
Okay, yeah.
And again, we'll talk more about the different packets as we go forward.
Okay.
So the data link is below that. And the data link divides data into frames that can actually be transmitted out on the network. A frame is the data structured for actually being sent out. And it includes what's called the payload, the raw data, the sender and receiver's network addresses, error checking, and then control information. So things that do happen at the data link layer, maybe not all the information was received. Well, it can possibly be corrected with error checking. There are 2 types of error checking to know about. A frame check sequence and then what's called CRC. And CRC is an acronym for cyclic redundancy check. And this goes back to that checksum I talked about earlier where we run that mathematical formula. That formula is actually called a CRC algorithm, or a cyclical redundancy check. So the data link layer controls the flow of information, which then allows the physical NIC, or the network card, to be able to process the data without error. The data link layer is divided into 2 sublayers. They're called the LLC and the MAC. And you notice MAC, that is where the term MAC address comes from, the Media Access Control Layer. And the reason for this is because the LLC kind of deals with the upper part and more with the layer 3 stuff. The MAC, at that point, you're dealing with more the physical side of things. So the MAC sublayer manages access to the physical medium, or the physical layer. And the physical address is the number associated with each network interface. Physical address, remember, is the same thing as MAC address or hardware address.
IP address.
No, IP address is a virtual address. That's a logical address, not a physical address. That's why I'm throwing those at y'all at the same time so you can get those straight. If I say a network address, then I'm talking about an IP address. I don't ever use the term, but if you see virtual address, they mean an IP address. But if they say a physical address or a MAC address or a hardware address, that's all your MAC address.
Because an IP address can change, MAC address is always going to be the same.
Right, MAC addresses are hard-coded into the cards. Every network card in every computer in here has got a MAC address that's been assigned to it by the manufacturer before it ever came out. So here they show the two layers and why there's two. LLC is at the top and it works directly with the network layer. And then MAC is at the bottom. And the MAC is going to frame everything so that when it gets to the physical layer, it can actually be sent out on the network. Here they're just showing a picture of a wireless card. Even wireless has MAC addresses. And on most cards, the MAC address is written on it. You can find your MAC address by typing ipconfig /all. And now my network, my computer has what looks like tons of different network cards in it. And the reason for that is I've got VirtualBox on here. And VirtualBox creates a different network address for every single virtual machine you have. So see, I have all of these with extra ones. But if I go down through them, I can find the one that I'm actually using right now. And I think I just passed it. Yeah, see, Dell Wireless, that's the one I'm actually connected to. So see there, my physical address. The MAC address for my laptop is 00265E481A1D7. Take some time and make sure you know how to recognize a MAC address. A question I got on my Network Plus exam, they gave me a list of 4 addresses and said which one of these is a valid MAC address. And one of them had too many numbers in it. One of them had a J in it. Remember, with hexadecimal, nothing's ever going to be above an F. One was too short, and one had just the right number. So
that's 10 numbers.
right, 2, 4, 6, 8, 10, 12.
12
We'll talk about all of these later, but here's my IP address. Above that, that's my IPv6 address. IPv6 looks completely different from IP. You see how it's a much larger number. And then it tells me here, I'm using DHCP, which DHCP is a way to not have to assign IP addresses. You have a server assign them to you. So it tells me here I was given this address at 2 o'clock today, and the lease expires at 2 o'clock tomorrow. So addresses are good on this. Yeah, I think I left it at the default on the wireless back there of 1 day. So then finally at the bottom we have the physical layer. And the physical layer accepts the data from the data link layer, and the physical layer actually generates the signals that are sent out on whatever media it is. That means if it's wireless, the physical layer is going to have the transmitter to actually send the data. If it's copper wire, it's going to generate the voltage to go out on copper. If it's fiber, physical is going to deal with the actual light pulses to send the data out. So the physical layer accepts and detects signals. It passes them on to the upper layer. It monitors the error rates, but notice no error checking takes place at the physical layer. The physical layer does not concern itself with errors. All it does is gathers the data and sends it to the data link layer. So if there's an error, the physical layer is going to send that right on like it is. Those zeros and ones are going to go right on the way they are. and it's going to rely on an upper layer to figure out what they are. Devices at the physical layer, hubs and repeaters. NICs operate at both the physical and the data link layer. And that's important because they're physical in that what's actually connected to it, but they're data link because they deal with MAC addresses. So I'm jumping ahead here, but I'm going to ask a question to see if y'all know it. Physical layer devices are hubs and repeaters, but a switch is a data link layer device. Why do you think that is? Do y'all know the difference in a hub and a switch? Okay, a hub sends out everything as is. A hub doesn't look at the data. A switch reads the MAC address off of a packet of data and only sends it to the port that it's destined for. That is why switches are more efficient than hubs, because they actually do read the data and only send it to the port that's necessary for it to go to. However, in order to do that, they've got to be able to see the MAC address. So that makes that not a physical device, it makes it a data link device. A hub sends the data no matter what to every port on it. You can kind of think about a hub as an old party line. I don't know if any of y'all ever lived way the heck out in the middle of nowhere and you had a party line. You pick up the phone, you know, and realize your neighbor's on it. Well, you just have to hang it up and wait. A hub is kind of like that. It's people sharing it. A switch is more like, you know, a neighborhood in a decent city where everybody's got their own phone line. So this is a good table of the OSI model. And this is slide number 45. What I would say do is just take some time and try to memorize this slide. On it, you're going to see the OSI model layers, the numbers, and the basic functions. I don't know what questions you will get on the test, but I can guarantee you you're going to get one or two that are going to be on OSI model. So make sure you know the numbers, kind of what's going on at the level, and the name. You know, I gave y'all two mnemonics. I don't care which one you use, but make sure you're able to write this table down as is. Especially knowing the numbers and the names will make it easier on the test. Oh, are you printing? Okay. Making sure that you're able to keep all of that separate is just going to be important. Especially layer 3, because you're going to learn in a minute. I said that switches are data link layer. Well, we have special hubs now that are managed hubs that are actually network layer. You can get devices that go on up. They make a layer 7 switch, which means that you're going to let the hub actually see what type of data it is that's transmitted and decide whether you want it to go on or not. Firewalls used to just be layer 3. A firewall used to just look at the IP address and say pass it or stop it. Now we have firewalls that are layer 7 devices, because you can tell a firewall to block all traffic that's streaming media, or to only allow traffic at certain times of the day, or, you know, block all BitTorrent traffic. That's a layer 7 thing. So the lines are kind of blurred now between where devices are and where they're going. So, all right. Communication between two systems. Data transformation, the original software application data differs from the application layer NIC data. Information is added at each layer. We have what are called PDUs, or protocol data units. And these are generated at the application layer. And the PDU goes down, and at each layer things happen. A PDU becomes a segment at the transport layer. It becomes a packet at the network layer. And then finally at the bottom, data link and physical, it's a frame. So encapsulation occurs at each of these levels. And encapsulation takes the data from the level above and wraps it into the layer below. What I mean by that is, like, let's look at network layer. Layer 3, the packet's got an IP address on it, an IP source and destination. When that reaches layer 2, the payload of layer 2 is that entire packet of data from layer 3, with a new header on the front of it and the end of it. And in that new header is going to be the physical address, destination, and source. And then finally, when it gets to a frame, that's what the physical layer transmits over the network. So here they're just showing that. At the top, I've got my data, and an application layer header gets put on it. At the presentation layer, a presentation header gets added, but the application layer is still there. So the application header and data is encapsulated at the presentation layer. Then a session header gets added, and that's an encapsulated packet of all the data above it. Finally, at the transport, data gets added on. Then below that, we get our network header, which is where our logical information gets added, our IP addresses. At data link, then we got that whole packet that gets put in the middle of that with a header and a trailer. And then at the bottom, the frame is the whole thing, and the frame is what actually gets sent out as the zeros and ones on the network. When that is received on the other end, the process reverses. The frame comes into the network at the destination. The data link header gets pulled off and sent up to the network. The network pulls its data off and sends it on up. So it goes all the way to the top, and ultimately the data reaches whatever the application is on the other computer.
So it always starts from 1 and goes to 7?
On the sending computer, it goes from 7 down to 1, and then on the receiving computer, it comes in at 1 and goes back up to 7. And in that first slide you saw where they showed the little lines with the virtual circuits. That was to show you that each layer on both sides is dealing with the same thing. If you're the sender, you're going to be the one that adds the network header. If you're the receiver, the network layer on the receiving is going to pull that header back off. So frames are composed of several smaller components or fields. Frame characteristics, this is the network type, and standard frames must follow. Ethernet is what we're using for the most part. Ethernet was developed by Xerox, and there are 4 types of Ethernet frames. The 802.3 standard is the most common, but there are some other ones. Token Ring is one. Token Ring was developed by IBM, and it relies on direct links and nodes between lines between each nodes. Token Ring is the 802.5 standard. Ethernet frames and Token Ring frames differ. They won't interact with each other because they're not the same in size. So the 802 project is the effort to standardize physical and logical network elements. 802.3 is Ethernet. One that you're probably all familiar with is 802.11. That is the wireless. And you know all the different types of wireless, A, B, G, and N. All of those are variations on that 802.11 standard. Now here is a table of some of the different ones. I don't think you're going to need to memorize this for the test, but be familiar with the common ones on here. Make sure you remember that 802.3 is Ethernet. Do know that 802.11 is wireless. And if you were to get a question on any of the other ones, it might be Token Ring, 802.5. But there are more of these than are listed here. There are tons of different Ethernet 802 standards. So that is kind of a summary, a quick rundown of the OSI. And the 802 project was, designed to standardize all of this. Do y'all have any questions over the OSI? The next chapters, as we go through this, will take those 7 layers of the OSI, and we'll develop each of them a little bit further. But just make sure you know the OSI model backwards and forwards, because that is going to be a huge chunk of the test. And just knowing that will really help you shortcut, all these other certifications you're going to take later. All right, so chapter 3, now we've got a general idea. We've started talking about the OSI. At this point, we've all got a model on how the network communicates, so we can start talking about what actually goes on. We're going to talk about some of the data transmission concepts. We're going to talk about physical cables. We're going to talk about the limitations of media, the principles behind cables, and we're going to talk about wiring standards. So, some basic terms to know. Transmit is the process of actually issuing signals out on the network. Transmission is the process of transmitting. And most network cards, especially wireless, use what is called a transceiver. And that is the device that actually transmits and receives the signals. So there are different types of signaling. There's analog and digital. And we don't have to get into too much of the electronics of this, but digital is a 0 and a 1. Computers use 0 and 1, so that makes it a perfect fit. An analog signal is one that actually travels along a wave, and the wave is constantly changing. Analog, you can think about your old AM radio. That's analog. If you don't have HD FM, if you've still got just over-the-air FM and not, Sirius or XM or any of those, that is still analog. Old TVs until the digital sunset took place were analog. So volt is, you can think of volt as electrical current pressure. Electrical signal strength is directly proportional to voltage. And the signals can be whatever based on the type of media. If we're using wireless, it's going to be electromagnetic waves. If we're using copper wire, it's going to be the current. It's going to be the voltage on the wire. If we're using fiber optic, it's going to be the actual pulses of light that get transmitted. So in analog, you've got that continuous voltage. Amplitude is the measure of strength at a given point in time. Frequency is the number of times the amplitude cycles. Wavelength is the distance between one peak and the next. And phase is the progress of the wave compared to a fixed point. And there's a graphic coming up that'll explain that. Here is just a typical analog transmission. And you see here we've got a peak amplitude is from the middle to our positive point or going the other way down to our negative. Here they're showing that you've got two signals with what they call a 90-degree phase difference. And what that means is if you look at this, two waves sent at the same time, when one is at its highest, the other is at its lowest. So analog does have some benefits over digital. Even though we live in a digital world and digital is taken over, analog signals are more variable. They can convey greater subtleties with less energy. The drawback is that imprecise voltage makes them susceptible to transmission flaws. Some people think that, like in music, for example, because analog has all the little subtleties of not being just on or off, not being 0 or 1, there's a lot of people that still buy like records, for example, because that's an analog technology, and for big audio people, they say the sound of a record is unmatched because all of those subtleties are there when it was recorded. Digital, is just an on or an off. Digital is represented, positive voltage is a 1, a 0 voltage is a 0. Here is an example of a digital signal, and you see it's 1 0 1 0 1 0. All right, so something that I need to show y'all how to do is how to convert between analog and binary and decimal. And They show a different way on here, but I'm going to show you an easier way than what they show you. So, and I'll just have to draw this and scan it so I can put it on the slides for y'all. But the easiest way, I think, to convert from binary to decimal and decimal to binary, there is a table you can draw. And if you start drawing it, you start with the number 1. And double it every time. Draw it all the way over to 128. You start with 1 and double it every single time. So 1 is 2, then 2, 4, 8, 16, 32, 64, 128. If I give you a binary number, I give you the number 100100001. In order to convert that to decimal, if you draw on the table, all you got to do is add up the values of where that number falls in the table. So this number in decimal is 128 plus 16 plus 1. Somebody do the math. What is that?
145.
What is it?
145.
145. Does everybody see how we got that? All we're doing is adding up the numbers of where it falls. Now to go the other way, if I give you a number 180 and say convert that to binary, you start at this side of the table, and is that number greater than or equal to the number you've got to start with? So is 128, is 180 greater than 128?
Yes.
It is, so that gets a 1. Now subtract that value from your first number. What's 180 minus 128? I'm not a math person, that's why I'm making y'all do this.
52.
52? Okay, 52 is not greater than 64, so 64 gets a 0. It is greater than 32, 32 gets a 1. 32 minus 52.
1.
All right, is that greater than 16?
Yes.
That gets a 1. We'll subtract 16. What does that leave us? 4. It's not greater than 8. It's greater than or equal to 4, so that gets a 1. So 4 minus 4 is 0, so the rest of them get a 0. So does that make sense to y'all? Do y'all know how, are y'all following that? This is something you're going to have to know how to do. They're going to give you numbers on this test, and they're going to say convert it from binary to decimal or decimal to binary. So the way that I say do it is just memorize this little table, and it'll be real easy for you.
So that's the decimal level, 180.
180 is what I started with, yeah.
That's the decimal.
Right. And see, you can always go back and check your work. If you're not sure you did it right, 128, 32, 16, and 4. If you add those up, if we did it all right, it should be 180.
Is it always in that order, starting from one from the right and working on the left? It's always in that order?
Yeah, it's always in that order.
So you your 1, 0, 1, 1, 0, 1, it would always fall into the first one would be 128.
Right,
Second
right.
one, 32.
yeah,
Because they've got different bits, like a 5th bit or 7th bit.
right.
Should be
For
enough.
all of these tests, you're never going to be asked to convert a number bigger than that. And the reason is this is Network Plus. The maximum number an IP address can have is because of this binary. The largest IP address you can have is 255, which is all ones all the way across. Or yeah. So does that kind of make sense to y'all now?
Yeah.
And you can either memorize the numbers on the table or just remember, start with a 1, draw it from right to left, double that number every time. If you were a math person, you can look at this as this.
Exponent.
Right. 2 to the first is 2. 2 to 0. Remember, any number to the 0 power is 1. 2 to the first is 2. 2 to the second power is 4. 2 to the third is 8. 2 to the fourth is 16. Me not being a math person, though, I don't want to remember what 2 to the fifth is. I just know if I draw that table starting at 1 and double it, I'll get it. You won't be asked to for this test, but you could go on with this. After 128, we'd have 256, then 512, then 1024. So if you had a larger binary number you needed to convert, you could draw your table on out as far as you needed to, just doubling it every single time. That is also why in computers we don't use like numbers that are rounded off. A megabyte of memory is not actually 1,000 kilobytes. It's 1,024. And the reason for that is if we drew our binary table over that far, 128, the next thing's 256, the next thing's 512. After that, what? 1024. That's why there's 1024 kilobytes in a megabyte, not 1,000. It's all because binary, and remember, computers are amazing, but they're really stupid if you think about it. They don't do anything but deal with a 0 and a 1. They don't know anything else. There's nothing else to them. Okay, so digital is more reliable, less noise interface. The digital drawback, though, is many pulses are required to transmit the same information. Digital requires overhead. So modulation is the way that you transmit data. And data relies on digital transmission. So if you're going to transmit data over an analog system, you have to have what's called a modem. And modem actually stands for modulator demodulator. And these came back in the early days of when they were first starting to try to network computers. Because when we first started networking, you know, they didn't want to have to run wire between all of these places they wanted to send things. So what was already in place? The phone system. And the phone system was analog. So they wrote something that would work on the phone system. So in modulation, you have a carrier wave, which is combined with another analog signal to produce a unique signal. That is then transmitted over the system from one node to another. The carrier wave conveys the information. The information wave is then added and modifies one property of the carrier wave. Frequency modulation is where you are modifying the data signal. Amplitude modulation is where the carrier signal is modified by the application of a data signal. An example of a technology that uses this is DSL. Here they're just showing an example of a carrier wave that's been modified. Another term to be aware of are simplex, half duplex, and full duplex. Simplex means the signal is only going to go in one direction. The FM radio I talked about earlier in your car, that is simplex. Your car doesn't transmit anything, it just receives it. Half duplex means you can send and receive, but not at the same time. CB radio, yeah, or walkie-talkie, or ham radio, that's all half duplex. You can send and you can receive, but you can't do it at the same time. Full duplex is what we use on computers and what the telephone system is. You can transmit and receive at the same time. Now, it's funny that can happen on a phone system because most of us can't talk and listen at the exact same time. But the phone system itself can actually handle us doing that if we could do it. So here's their example of that. Simplex data goes from the transmitter to the receiver. Half duplex, we've got an OR, transmitter to receiver, or turning it around, transmitter in the other way to receiver. And then finally in full duplex, we have an AND instead of an OR. I'm able to do both at the same time. So a channel is a communication path between nodes, and it's separated either physically or logically. This is how full duplex takes place. It uses two channels. You use one channel for transmit and one for receive. Multiplexing is taking multiple channels and sending them over one medium. You do that by using subchannels, which are smaller channels, and you have these devices that are called muxes and demuxes. And a mux combines all those signals, and a demux separates them back out. The best example I have of mux and demux, on the old analog cable system, a mux was what you had on one end that put all of the channels into one wire, that allowed you at your house to be able to watch all the different channels. And your cable box or your TV, if you didn't even have a cable box, is the demux, because you were just looking at each individual piece of data, even though it had all been put in the same wire at different frequencies. Nowadays that the cable system is digital, the rules are a little different, because there's very little analog left on it. So here is a type of multiplexing. This is called time division. And in time division, you see everyone is given a slot to send their data in. A got the first slot, B the second, C, and this one we're only muxing 3 signals. So each one gets a slot. The problem with time division multiplexing is that the slot is given to you whether you need it or not. So it might be inefficient if you've got one device that only transmits stuff every once in a while, and other devices that need to transmit all the time. You're wasting those time spots. Statistical is a type of multiplexing where you are breaking it up by priority and by need. In this case, A doesn't have very much data. B got more priority, so you see there's 3 B packets every time for 1 A packet. Frequency division multiplexing is another type, and this is where we use a unique frequency band for each subchannel. Your cell phones use these. That's how we're able to send all the data out on the cell phone network. Everybody's on a separate channel. Wavelength is one that's used in fiber optics. And then dense wavelength division multiplexing is used on modern fiber optic networks, and it gives extraordinary capacity. So in sending data from one point to the other, you have a point-to-point transmission, which means one sender is sending something destined for one receiver. Point to multipoint, one sender is sending something destined to multiple receivers. And then a broadcast where one transmitter is sending it to an undefined number of receivers. Point-to-point might be something like if you've got someone on a telephone call. That's one conversation you're making with someone. Point to multipoint might be if you've done a 3-way call. You've got 2 people on it. Broadcast can kind of be like this class. I'm sending it to y'all because y'all are listening, but if other people were in here, they'd be listening as well. So they would kind of hear the same thing. Here's a graphic just kind of showing what they mean by that. And in broadcast up here, they've got point-to-point where they're sending data between two buildings. Point to multipoint, they've got a tower on a building sending it to multiple homes. So there are 2 terms to be aware of, throughput and bandwidth. Throughput is the amount of data transmitted at any given period of time. It is expressed in bits per second. Bandwidth is the difference between the highest and the lowest frequencies, and it's measured in hertz. Now, they want you to know that is the strict definition, but in reality, people use the term throughput and bandwidth interchangeably. If I ask you how fast your cable modem is, I'm probably going to say, what bandwidth are you getting? and you may tell me you got a 10 meg connection or a 30 meg connection. But in reality, what you're actually telling me is your throughput, not your bandwidth. So here are some of the measures, and they've rounded them off in decimal. A bit, BPS, kilobit, kbps, megabit B, gigabit above that, and terabit above that. Now they've rounded them in decimal, but like I said, in reality, that number is not 1,000. That number is 1,024. We've then got baseband and broadband. Baseband, the digital signals are sent through direct current pulses applied to a wire. It requires exclusive use of the wire's capacity. One channel can be transmitted at a time. An example of baseband is Ethernet. Broadband is signals modulated as radio frequencies. They use different frequencies. They do not encode the information as digital pulses. Broadband, a good example is your cable. Your cable's using all kinds of different frequencies. The reason baseband is okay for Ethernet is that even though it sounds bad here because you say only one thing can be sent at a time, remember every computer in here's got a separate wire. So they're all able to communicate at the same time because they're all on separate wires. Noise is what happens when the signal gets garbled because some sort of interference takes place. And the majority of noise in an Ethernet network is EMI. And EMI means electromagnetical interference. One thing that is a major problem to unshielded twisted pair wire like we use in here is fluorescent lighting. Our wires are run up in the ceiling, and they do run back there to the back. And it's a short run, but I don't really know. I hope they didn't. But if they ran the wires over the top of these lights and one of these bulbs is going out, it'll give you all kinds of interference on your network. So you have to kind of run your wires. If you're doing it properly, you want to go around them. Like in here, what they should have done is probably run the wires all the way down the wall and over. And for that side, all the way down that wire to the back and over to the switch. Because if you go across those lights, you'll have some trouble. Right, yeah, all of that does cause a problem too, you're right. Security systems, anything that's got magnetic interference can cause trouble. It's funny how noise can affect in ways that you don't think of. We were having some major problems at the juvenile court with our internet. And we had business class cable over there. And it had run fine for 2 or 3 years without any trouble. And then after the 4th of July one year, we started having some issues. And at first, they weren't so bad. They were just when it would rain, something would act up, it would go out, I'd drop it. And it got worse and worse. And I'd had the cable company looking. It was the weirdest thing. The signal would get great, and then it would drop. We'd get more and more noise in it. Well, finally, after about 2 weeks of trouble and us threatening to change companies if they didn't come do something about it, I got them out there. And they traced the wire, and the wire for the juvenile court in Shreveport, I don't know if y'all know where it is over there on on Market. It's not quite Uri yet, it's still Market, but yeah, basically Uri Drive. It's fed by that neighborhood. The cable runs into the juvenile court from the neighborhood behind it. Somebody over the 4th of July had shot a bottle rocket up into one of the wires, and it had melted a little piece off of the shielding on the cable wire. And it was also, but somebody over there was playing with a CB radio at night, and the shielding missing on the wire was enough that we were getting interference into the wire from somebody playing with their CB radio at night, and when it would rain, it was shorting it out. But it wasn't enough to affect TV, and most of those people over there had TV, most of them didn't have internet. So nobody else had reported the issue because TV was fine, but internet uses a higher set of frequencies and it's more susceptible to the noise. So yeah, random little things like that that you find that you never would have thought about. Crosstalk is a problem where wires actually in the wire, the different wires that make up a piece of twisted pair, interfere with each other. And the way that you deal with that, the reason we have twisted pair instead of straight wire is twisting those wires keeps them from interfering with each other. So that's why, like, I'll bring a piece of cable and let y'all take it apart and look at it. But that's why the individual wires in it are twisted together into sets of 2. Do what now?
You saw that connection earlier.
So here is a piece of a wire. They're showing crosstalk. One wire is transmitting, and because it's electromagnetic, it interferes with the other wires. Attenuation is the loss of the signal strength as it travels away from the source. Attenuation happens on all electromagnetic wire. That is why there's a limit on how long the wire can be in Ethernet. 100 meters is the point where the attenuation reaches a point that you can't read the signal anymore. Well, and that's theoretical, I'm going to say, but they want you to think 100 meters is the maximum length. You can get away with a wire being a little bit longer, but it's out of what they call specification. By that, it means that it's not guaranteed to work. It's not up to the standard. I had a wire at the juvenile court that was 120 meters, and it worked just fine. But it was over what it should have been. You know, I should have put a repeater in there for it to be that long. There are ways to boost the signal. Analog-wise, you can pass it through an amplifier. If it's a digital signal, you can repeat the signal with a regenerator. So here they're showing the difference in an analog and a digital when it's repeated. In an analog, if you have an amplifier, you'll notice the signal afterwards, you've just amplified the noise. Digital, though, when you have a repeater, you regenerate the signal. So that's one reason digital is better. You've taken the noise back out of it. Latency is a delay between the signal being sent and being received. Causes of latency can be the length of the cable or an interconnected device. And you have what's called a round trip time. That is the time for a packet to go from the sender to the receiver and back. And the easiest example I can give you of round trip time, you can check it with the command ping. If I ping google.com, for example, that time is the amount of time it took for the signal to leave my computer, to reach the server at Google, and to come back to my computer. So you see it did it relatively quick, 62 milliseconds. When you are selecting media, some things you've got to look at. The throughput you need, the cost, the noise immunity, the scalability, and the connectors and the media converters. For the most part, the wire that most of you are probably going to work with most of your time is going to be unshielded twisted pair. That's this wire that we've got running around the rooms here and everywhere on this campus. It is not the best choice, but it is cheap. And because it's cheap, we accept that there will be some noise in it, that there will be some problems. But it is so much cheaper than it would be to run fiber to everywhere that we put up with it. Fiber doesn't care. You could run fiber right over the top of these lights or right next to a security system and it wouldn't make a hill of beans. But fiber's money, right. Fiber has come down greatly in price, but there was a time when a fiber wire was probably 15 or 20 times what an unshielded twisted pair wire was. And we have run out of time. So I'm going to stop. We're on slide 36. We will pick it up with throughput next time in Chapter 3. Go ahead and do that pretest when y'all get home. And start, if you have time this weekend, start looking at your exam cram questions. Remember, by the end of the course, I'm going to have wanted you to do 60 questions in each section on the Cram Master. So I want y'all to start working on those, a few every day. And any of them that you have questions on, screenshot it and bring it to me. At the first of every class, we'll talk about any of them y'all have questions on. So do y'all have any questions or?
I'm just getting to my crown master, used to some like to work with it later.
Play around with it some. It's easy once you work with it. Now that you've all got it, next time I'll do a little kind of a quick rundown as we start on Cram Master so y'all know how to get in it and move around on it. But I think y'all will all be able to figure out the pretest pretty easy. It's 50 questions. I don't think it'll take you more than a half hour at the most to do. So, all right. Well, y'all have a good weekend, and I'll see y'all on Monday.